Okay. So yeah, so we were reviewing this paper, cartographer paper. So okay, so far I think yeah, what we have done is we have gone over little bit basics of SLAM and basics of graph SLAM, understanding local SLAM, global SLAM. I'll quickly go over the slides in 2 minutes. So last time we talked about these things, the 4 different verticals, why cartographer is an important paper, and we went over the SLAM basics, that we have controls and observations, and we would like to find map and robot pose in SLAM. And in graph SLAM, you kind of using the poses as nodes, and you using successive and non-successive or loop closing constraints. We add edges and based edges between the poses, and now solve this graph as an optimization problem. So I think last time one question that was asked is ki what's the error? How is, so I think here, okay, I'll go forward and then I'll answer. Anyways, so then yeah, there's a two in GraphSlam there are two parts, front end and back end. Typically front end is what's also present in local SLAM, where they do scan matching, similar to this, like consecutively do scan matching and do get pose estimates, and then back end they try to, based on the graph that is formed, they try to minimize the loop closing constraints, so that the successive pose constraints or successive pose errors are also not increased. So that's what the goal of graph slam in local slam. So we saw that how cartographer improves upon or uses an improved version of Hector slam's formulation of scan matching. So we saw that given this previous scan points and next scan point, we find map values on the next scan point and tries to make it match. And if we try to minimize this, so what it means is that for every next scan point, we ensure that it falls on at least one of the previous scan points that has high map value. So what does high map value mean? So of course in your occupancy grid value, so map value is nothing but your probability value. In your occupancy grid, you keep on increasing or reducing your map value based on your LIDAR scan. So if your LIDAR has been reflected from some of these voxels, you increase the probability of being blocked or occupied. And if the LIDAR rays, if you know that LIDAR rays have passed through some of the voxels, you reduce those probabilities. So essentially here in scan matching, you for a set of previous scans or for a map and given new scan, to get a pose estimate of new scan next scan point with respect to previous map or pose, you try to match next scan points with the these high probability occupied map points in Hector slam. So that's what it that's how it applies scan matching. And in global slam, yeah, you try to find the non-successive loop closing constraints, and your goal is to minimize loop closing errors. So I think one of the questions that was asked is, what does a loop closing error means and how can it be visualized? So just to quickly understand, so how we find that is, um, of course there are a good number of resources that say show how to calculate loop closing errors. So let us consider these two. So in a GraphSlam setting, let us consider these two nodes, that is xi and xj, and let these be uh, two non-successive nodes. So let xi be this and let xj be this. So essentially xj, we estimated xj or we got xj after doing multiple successive pose estimates from xi. So if that was xi, we did pose estimate of this from here, like that, from here. So indirectly, we have done a pose estimate of xj from xi via these successive poses. So that's one pose estimate of uh, one pose estimate of xj with respect to xi. The second is, now that we know that we are seeing that xj and xi are in the same part of the environment, their scans will contain similar or most of the same set of points. So now what you can do, there is one that there is one relation that is directly how xj is with respect to xi, using these set of intermediate points. But since now we are also looking at the same part of the environment, we can directly compute a scan matching or pose estimate of xj with respect to xi, because they are in the same part of the environment. And let's say if we do that, now if we directly try to estimate the position of this xj point from xi directly without using intermediate, then we find that maybe because there were some errors that were accumulated, they don't the scan matching estimated for xj from xi is not exact, and it turns out to be zij. So zij is the pose estimate that we obtained for xj when measuring compared to xi. So now, so essentially in an ideal setting, if there were no slam errors, zij should have been equal to xj, but because some errors have kept on accumulating, and when we finally revisit a scene and we try to do scan matching between non-successive poses, we see this error. So this difference between zij and xj, that is your eij, is what we call as loop closing errors. And of course we can write a square equation that is based on the sensor noise. So omega ij here is the noise in the sensor, and based on this we can the post graph formulation is solved. So the goal of the post graph formulation is, so eij also contains the poses or the pose uncertainties that pose uncertainty errors that may have accumulated in the successive poses also, or in these constraints. So every constraint gives an eij in this equation, and typically the loop closing errors are much bigger than the successive pose errors that are reflected. So by trying to solve this post graph equation, we actually end up trying to minimize these loop closing errors, which are typically quite high. That's exactly what we saw even in this simulation, that we try to minimize these loop closing constraints such that such that any two successive poses are still highly connected to each other. So here we'll see that as it is going, there are multiple jumps. Yeah. So as it keeps on forming loops on other nodes, and it also is I think we'll see a jump. Yeah, so jumps that we are seeing, that is because it's making corrections, and it's making corrections on the fly. Yeah, so the jump we saw in all the nodes is it tried to evaluate a pose such that the loop closing errors are minimized, but also the successive poses are also in line with each other. So yeah, the jump that we saw there, that was the big jump we saw, that was trying to correct for all the poses such that loop. So essentially this is trying to bring it closer to its real point by trying to minimize this loop closing error or the loop closing error constraint to all the successive poses. So that's the graph based SLAM. So any questions so far, any previous questions that anyone has on the SLAM basics, graph SLAM and all, before we go deep into Cartographer? Okay, so I guess no questions. We'll continue. Yeah. Okay. So yeah. So Cartographer, the main goal is to do. Key novelty comes in how they find this. So essentially, the main goal in Cartographer or the key novelty is that how do you find these loop closing constraints? Like how do you do the scan matching efficiently, and what are the thresholds? So one of the questions that was asked yesterday is what is one of the thresholds that for which we should consider scan matching? Like I said, that the naive way would be, for this you can do scan matching with every previous non-successive pose. But should we do scan matching with every previous pose, or maybe pose that are just nearby, or maybe and let's say if you so one is that with which poses should you be computing your your loop closing constraints with? And let's say if you decide to compute loop closing constraint with this and with this, and you get a similarity score here between this and this pose of, let's say, about like that this and this pose are in the same environment, the similarity score that these two poses are in the same environment falls for somewhere like around 0.8, and for this and this falls for somewhere around 0.2. Then at what thresholds do you decide that we will consider this constraint but not consider this constraint? Because having too many bogus constraints can also, let's say if I just try to have bogus constraints, even if I try to weight it by the amount of similarity in environment. Now, of course, if you weight it by similarity by in the environment, it helps, but we actually end up wasting time trying to find a lot of these bogus constraints. And what kind of thresholds should we have to consider to see if the match in the environment of two poses are valid for adding a constraint or not. So all these things is what we'll be discussing next. Okay, so essentially, yeah, so to find loop closing constraints, one of the simplest way that we could do is, let's say for this pose, we would like to know which other poses should we consider to find the loop closing constraints. So what we can do is we can just draw a square, a search window around this pose, and all the poses that maybe fall under. So the size of the search window is a kind of an hyperparameter here, but all the poses that fall in this search window will be considered for for considered a candidate whether a loop closing constraint should be added with that or not. So for computing loop closing constraints, those are considered candidates. So what we can do is, so you can see that this search window goes from in both x and y axes as from -0.2 to 0.2, and so here wx is the search window in one direction for x direction, x axis, and wy is for y axis. So essentially, you want your search window from -wx to wx and -wi to wy, and at 0, 0 is let's say your this xj pose is sitting. Okay, and xj pose is sitting, and then you try to find which of the poses. Now here what we were trying to do is that we were given the next scan points, we try to find such a pose estimate, such a pose estimate, or pose difference between next and previous scan, such that using that pose, if we were to transform all the points of second scan or next scan, it exactly aligns with the previous map or previous scan. So we would like to find this kind of a pose estimate. Now, instead of trying to, and definitely solving this cost function for epsilon gives us a value that best aligns the next scan points with the high probability previous map points or previous scan point. Now, of course, this can be scanned. We can use any optimizer to solve this. Another way to solve this would be to instead of trying to applying some kind of an SGD and trying to find, what we could also do is in a brute force manner, we could maybe in some form of a grid search. If in machine learning, in hyperparameter tuning, we use something called as grid search. So in some sense of a grid search, we could have a range of epsilon values and a range of epsilon x, epsilon y, epsilon theta values. And what we could do is, in a brute force, like in a grid search pattern, we could evaluate at each of those points. That is, let this represent that grid. So each of these points contains an epsilon x and epsilon y, and the point also considers the range of epsilon theta also, the different ranges of theta that it can take. And at each of the points, so essentially, what I'm showing you here is a 2D search window, but it's actually a 3D search window. 3D because the 3 dimensions are epsilon, pose in x, pose estimation in x, y, and theta. So what we could do is, instead of directly trying to solve using SGD, what we can do is, if we are sure that the optimal epsilon x, y, z is somewhere in this search window, we could actually query each of these search windows in a grid search manner, linearly or maybe in parallel. We can query each of these search windows, and each of the we can query each of these points, each point representing a pose estimate, and for whichever point, whichever pose exactly tries to minimize this equation, we consider that point, that pose, to be our optimal point. So why would we like to do something like a brute force is because we know, like we discussed, that even in Hector SLAM, what might also sometimes happen is that it can also get stuck in local minima. But now that we know that our global minima is somewhere in this zone, and by querying all the points, we are in some sense guaranteed to find that global minima or the global optimal solution that best tries to minimize this equation. So any question so far on what this grid means, or how this grid can be used in a brute force manner to solve this equation for scan matching? Any questions? All good?
What are the points? How did you get that points?
What are the points? Okay, so essentially what you can imagine is, okay, so okay, let's say, okay, let's imagine like this, right? Okay, let's imagine this. This is your, let's say these are your scan endpoints, okay, and of previous scan, and this is the scan, let's say endpoint of next scan. Okay, now let's say this is my initial estimate of next scan pose. Okay, by using some pose estimate, let's say epsilon naught, I have applied transformation on the next scan points, and it has reached here. Okay, now I know that given if I draw a search window around this PM, let's say initial point, I would like to find such a pose that helps me directly align it to here
with the previous scan.
Yeah, so essentially, yes, exactly, with the previously scan. So essentially what Hector SLAM methods were trying to do, they were trying to use, let's say, Newton's method or SGD to help get an epsilon such that if you add to the epsilon naught here, it goes from here to here. Okay, so using SGD and all, but we discussed that using, that even when you are trying to optimize, or if you use any optimizer, these surfaces may or may not be convex, which means in a non-convex setting, it may, instead of going here, it could also, let's say, go here, or it could also go somewhere else, so that maybe some other points are benefited. Right, because here we are trying to minimize over all the points. Instead of doing that, what we do is, not for this point, but essentially for the whole pose. Here I'm showing for a point, but essentially for the whole pose, I kind of try to draw a search window. And at every grid point in the search window, I say, is that a correct epsilon or not?
No, grid point is like virtual point, like you are equally spaced.
Yes, these are equally spaced grid points. So essentially, I am saying, let's say this is where my PM was, okay, and maybe this is where my P0 was, but I don't know that P0 is here.
P0 is 0th scan, PM is mth scan, like that.
PM is the scan point for the next scan that we would like to align with the previous scan.
Yes, correct. What is P0?
P0 are the scan points of previous scan.
No, that's what I'm telling. Like, then what about previous to previous? That are already aligned.
Yes.
Okay.
We are just considering in scan matching, just consider
two consecutive scans.
Yeah, two consecutive scans or a map to a scan.
Okay.
Okay, let's not think about map if that's confusing. Scan between two scans.
Okay.
Okay, so our goal is, so essentially, okay, in simple setting.
No, this I understood. Here, why are they considering such a big grid? Like usually it should, like only nearby points will be matched, right?
Yes, exactly. No, okay. So these points are candidate pose solutions for this problem.
Okay.
So essentially, okay, how can you solve this? You can either solve it by applying SGD on this.
Okay. Or just get all the possible values.
All the possible epsilons and just substitute in this equation and see which gives you minimum. Okay, and whichever gives you minimum is the correct epsilon or the correct pose estimate for you.
Yeah, correct.
Okay, great. Any questions? Any other questions on just the grid part? Or so here each of these points
so this point is formed from that equation, epsilon, previous equation, this equation.
Yeah, I'll come to that, how those points are formed. But essentially you can imagine that we can create a search window from let's say, okay, in SGD what you do, you start with an epsilon and epsilon naught, and then try to go to the next possible best solution based on maybe gradient, or in Newton-Raphson you follow other methods to go to the next best epsilon candidate, right? But here, what you do is allow around epsilon naught, you just query, you just take collection of all the epsilons and just put in the equation and see which epsilon value around epsilon naught gives you the minimum for this cost function.
That is brute force.
That is brute force.
Yeah.
Right.
How do we get this collection of epsilons?
Yeah, I'll come to that. How do we get? But intuitively, I'll show you using equations how we get. But intuitively, you can understand, right, that if we start with an epsilon naught, you can maybe just look 10 points ahead and 10 points ahead and 10 points backward in both axes and just form a grid kind of thing. So this is something similar to, if you remember in your hyperparameter tuning, where you do grid search. In grid search, you just around some, let's say some hyperparameter, you just vary the hyperparameters in forward direction and reverse direction for all the variables. And then for every combination, you try it on your machine learning model and then check that for which hyperparameter tuple does it give the minimum value. So the intuition is clear, right?
Yeah, so I'll just summarize it. So let's say you're on some pose M and you want to find whether it's a loop closing pose or not. So what you'll do is you look at the previous 10 poses, let's say M minus 1, M minus 2, M minus 3 to M minus 10, and then for each of those points, so each of those points will have some epsilon, some coordinate epsilon, and you will use those epsilons and try to find and compare it with the mth points epsilon to see whichever gives the lowest loss. And
no. Okay, so a small correction to that is, okay, great that you tried saying that. So essentially, when I was trying to explain this grade, here I'm only concerned between applying scan matching in two poses. So I think what I'm trying to explain here is, so we understood the Hector Slam's setting of scan matching. Now we are going towards like we are using the, so essentially in Hector Slam scan matching, we are trying to do scan matching between two poses. So we are not saying if they are loop closing constraints or not. Let us assume that for any given two poses, if we want to, and they are, let's say, nearby poses, because either they are successive or maybe they are candidate loop closing constraint poses. But between any two poses, if we would like to do scan matching, what would be an alternate way or a brute force way of doing scan matching is what I was kind of describing. So when I said look at 10 points ahead and 10 points back, I did not mean 10 points ahead pose or 10 points back. I meant, okay, so what I mean is, let's say this pose and this pose are in the same environment, and maybe these two, and we would like to get scan matching between these two. Now the simplest method would be to, what we can do is we can do a Hector Slam like formulation, have a map value for previous scan, and then try to minimize this using some optimizer, right, between this pose and this pose. Now, instead of doing this, now what's the issue of doing this is that this already contains like this sometimes can give you local optima like solutions, or may not give you the best optimal solution for the problem. So maybe this pose and this pose are offset with each other by, let's say, 2,3. Okay, maybe if this is at 0,0 and the actual in ground truth, this is maybe 2,3. But when you apply, let's say, Hector Slam like formulation, you get something like 2.5, 2.5. So there's error in estimate of this pose with respect to this pose. Okay, so we understand why that happens in Hector Slam, right? Because this may be a non-convex surface and it could result in local optimas. So why is it non-convex? Well, by the way, you can see that this is a squared norm here, but still why I'm calling it is non-convex, it's because the correspondence may not be perfect. This loss in itself is definitely will converge to a good optima, but the correspondence, so we don't, since Hector slam does not care about correspondence, maybe PM was supposed to go with P10, but it ends up going with P00. So because of those issues, what we would like to do is, best thing would be to try in a brute force manner. That let's say if PM were to go a little here, or PM were to go a little here, PM were to go a little here, PM were to go a little here, and like that we evaluate the complete place, and we keep sending PM to those places, and PM, that is, so PM is moving means all the points in second scan are by transformed by that much pose, little bit, and as a result of that, then we see did that epsilon. So let's say from here we moved by this much epsilon, by here we moved, let's say from here we moved to epsilon 1, from here we moved epsilon 2, epsilon 3, 5, 6, 10, and maybe we found it at epsilon 7. Whenever all the scan points were transformed of second scan were transformed by epsilon 7, that resulted in the minimum value for this equation. So by that we got that epsilon 7 is a, so did I confuse you more, or did you understand what I was saying?
I kind of understood. So let's say I found the epsilon which gives me the minimum loss function. After that, what happens? Like, is there some sort of a weight update step, or?
Okay, no, okay. So if you have found that, yeah, okay. So okay, it's not a way, since you have already found the epsilon that gives you minima for this value. So essentially your now goal becomes so essentially you have solved the problem. So that is the pose that you were trying to find, the pose of second scan with respect to previous scan. So that is your solution.
Okay.
But should I repeat?
No. I think it's fine. Like, if I have questions, I'll ask like in the future when you like talk about different topics.
So essentially, you can understand this like maybe you can think of this as your, let's say, machine learning system, okay? And you can think of these epsilon, x, y, theta as hyperparameters in your machine learning system. And what you would like to do is find a tuple of hyperparameters values which best minimizes or which brings the least loss value in your machine learning. So what would you do in a grid search? What you would do is you would vary the epsilon x and you would, for different values of epsilon x, epsilon y, and epsilon theta, you will try those individually different values, and then ultimately one tuple comes out to be a winner, right, in a grid search setting.
Yeah.
So similar to that, the way we just found, the optimal hyperparameters in by applying grid search in epsilon x, y. So the hyperparameters being epsilon x, y, theta here, analogous to. So the optimal hyperparameters that we obtain for our machine learning system by trying different hyperparameters in a grid search like fashion, not the random search, the grid search like fashion. Analogous to that, here we try different epsilon x, y, and theta values so that we can minimize this equation. And if once we have found that epsilon x, y, theta that best minimizes this equation, we say that is the exact pose estimate or pose offset between previous scan and the next scan, because that is what minimized this equation. Okay. Any small question, any doubt?
So all of this happens in real time as the bot is moving.
For every, yeah. So if you would like to do a scan matching, I mean, of course, I mean, I'm just explaining the method here of brute force. Of course, if you would like to do brute force, it takes a lot of time, and it may not be real time, because you would have to evaluate at each of, so essentially each of this in a grid search, each of these points is a possible candidate point that can minimize this. So I'm not sure if brute force can happen in real time, but the only advantage here is that because of brute force, you will not be stuck in, you are highly likely to not get stuck in local minima. That might happen in Hector slam. And secondly, yeah, and secondly, this is highly parallelizable. So maybe in a GPU like setting, you just have to like, and computing these values are not very difficult. In a GPU like setting, every core could just compute this for a given point and see if that's the candidate force, and then it can do. So those are the advantages, but I'm not sure. So definitely we'll build on top of this for Cartographer, but yeah, but this is why we would like to go to brute force. Two reasons. First being, we want the global optimal solution that best aligns the two scan point. And secondly, definitely this is a little bit parallelizable, but the more of our interest is we want to be accurate. We'll see how we can be computationally efficient in the later slides. Okay.
Yeah, I got it.
Okay. So yeah. So okay. So here what we are talking is, let's say you are okay. So of course, maybe what you have decided, what so far what we have done is, for this pose, we have decided that this is another pose that we would like to find loop closing constraint with, or maybe find the pose estimate between them. And now what we are trying to do is, we are trying to do a pose estimate, or we are trying to do scan matching between these two poses. And in this, while trying to do scan matching between these two poses only, not considering the rest of the poses, in just between these two poses, we try to draw a search window which is of the sides wx and wy. And in this search window, in a grid search like pattern, we try each of these points in the equation and see that which point gives us the minimum value, and whichever like grid search, whichever point post point gives us the minimum value, that is what we say as the optimal solution. So now we have slightly changed the flavor of how we were trying to solve for this scan matching equation. Okay, so okay, another point to note is that here what we are trying to do is, we are trying to minimize 1 minus map value of 1 minus map value of this second scans post point, a second scan point. Or what we are trying to do is, we are trying to ensure that all these second scan next scan points should get a probability map value, or a map value equal to 1, or higher the better, right? So by trying, so that is what, so essentially this gets solved, or the optimal lies when the map value at all the points are close to 1. Now, instead of trying to minimize for this, what we could also do is, we could, instead of trying to minimize for 1 minus map value, we could directly try to maximize for this map value, right? So because our simple goal is, if this point ends up lying on one of these points, then the map value is close to 1. So instead of trying to ensure that PM is always close to 1, or is exactly equal to 1, we can say higher the better. So this can be rewritten as this. Okay, is that point clear? That how this was converted to this?
Yeah.
Vanshil? Okay, fine. Yeah. So yeah, so the first what we do is, we convert our minimization problem into a maximization problem here. So essentially we are saying that instead of trying to solve for 1 minus map value, we are trying to directly solve for the m map value and maximize that. So that is now what it becomes. So that equation becomes this, and here so the argmax, and there we were trying to we wanted argmax of epsilon. Now what we are doing, since we are just going to search in a search window this epsilon, we are going to say argmax such that the epsilon is probably one of the points in your grid, or in this search window of this grid. Okay, so what we are trying to do is we are going to try each of these epsilon points. So let's say this is 0, 0, maybe this is 0.1, 0.1, and this is 0.10, this will be 0.2, 0.1. So let's say we take 0.1, 0.1, apply, evaluate using this summation equation here and get the value for that. And again, we get a value for this point, get a value for that point. And for every point, we try to find the score or the value for this equation. And at whichever point we get the maximum score, we say that that point or that epsilon, maybe let's say this is the point. So maybe, okay, or let's say this is the point. So in essence, 0.1, 0.2 pose estimate gives us the maxima. But here in the example, we can see that the highlighted, this is the highest highlighted region. So here we found that at about, I think, 0.06, minus 0.06 and 0.04. Actually, okay, no, minus 0.05 and 0.05. In minus 0.05 and 0.05 for that pose estimate. When we try to evaluate this equation, this gives the maximum value with respect compared to all other points. So we say that is our optimal point, or that is our epsilon star. Okay, and so what is small? So what is R? Okay, so I have, I think, shown here. R is the distance between two subsequent pose points. So essentially, R kind of determines the resolution of the grid that you are going to evaluate with. So if you have higher values of R, the points are going to be more spaced out, which means you are going to end up evaluating on less number of points, but you may miss a good minima. Maybe instead of getting this point, you probably get this point as an optimal solution, or this point as an optimal solution. But if you keep R very small, you do end up converging to the more closer to the real value in the brute force. So points clear so far? Okay, fine. So yeah, so Wx is the, so okay. And so what are small Wx? So these are your integers with which you multiply your R, that is the step size. So let's say from your 0, 0, you take this search window that represents, let's say, minus 10 to 10 in x-axis and minus 10 to 10 in y-axis. So essentially you have a grid of 100 points. And if you were to, let's say, multiply your grid with R here, multiply, so I think here it's coming. Yeah, so if you were to multiply with your step size, you would be evaluating at the exact point. So R into, so your Jx, Jy, J theta are nothing but Jx, Jy, J theta are nothing but different values that this can take. So since, and yeah, and you can also see that there is a third search window in the theta. So essentially what we have drawn here is a search window in X and Y direction. There is a third search window that is for every point. We vary the values of theta and try to evaluate that at what value of theta we are getting the minimum. Okay, so is the search window construction clear? Like, yeah. Any questions? Okay, so let's say, okay, I'll maybe try to give another example if someone may have any question. So let Wx be equal to 2 meters and Wy be equal to 2 meters, and R is equal to, let's say, 0.2, something like a 0.2 meters or 20 centimeters. And so what this gives us is Wx, Wy, W theta. We'll actually get Wx is equal to 10, which means the search window will vary from minus 10 to 10. That is minus 10, minus 9, minus 8, so on till 7, 8, 9, 10 in x-axis, similarly in y-axis, and similarly on theta. and so but on x and y axis you have step size. So let's say -10, you multiply that with the step size, you get exactly this point, or you get all the points on this line. Okay, so W bar is nothing but your search window, and these small wx that, okay, they're not very important right now, but they are the like the integers or discrete values of your search window. This these are the discrete values of the search window that you are going to evaluate on. Okay.
We only set the values. WX,
The capital WX, WY are hyperparameters. So you can set it as 2 meters, or so essentially it's like computational time versus accuracy trade-off. Bigger search window means you're more likely to get that, and otherwise not. And the simple W that we see here, that is essentially the transpose estimate that you would. So search window varies from, let's say, -10 to 10, but your actual values pose estimates will vary from maybe -2 to 2, -2 meters to 2 meters in both dimensions. So that is the kind of vary that we see here. So that is what we will feed. So W, all the values we are seeing epsilon naught plus this is, or the search window value is what we'll take, and each of these points is fed here, and then we try to see which epsilon, which value, which grid point here, or which point in this set gives us the maximum value, and that point is the final solution, epsilon star. Okay. Now the problem with branch and bound, and I think one of the, of course, simplest questions that was asked is that if we, and like even in a grid search like setting, if we try to evaluate on all these points, it takes a lot of time. So can we try to do better than that? So it turns out that even in cartographer paper, they have said that for just doing this scan matching, between previous and next scan, for trying to solve for this equation, you can, instead of trying to search in a whole of grid in a brute force manner, what you could do is you could partition the grid recursively, and after partitioning, you could actually figure out that in which partitions to look at, which partitions to not look at, and maybe you could prune away some of the useless partitions and just look at prospective good partitions. And as a result of that, instead of searching in whole of the grid, you can only search in a small part of the grid. Okay, so that is what branch and bound is now going to help you. So any questions so far before we switch gears and revisit branch and bound? Vanshi, Lakshaj?
Cool. I'm good.
Okay, fine. And of course, you're free to ask questions anytime later. Okay. We'll quickly revisit branch and bound, wherein yeah. So what happens in branch and bound is, let's say we are trying to solve. What is this? Yeah. Let's say we are trying to solve this 0-1 knapsack problem. So I think you guys a lot of you may be familiar with this. So let's say we are trying to solve this 0-1 knapsack problem, and if we have, let's say, a bag. So essentially the problem that we're trying to solve is, let's say if you have a bag whose maximum weight capacity is, let's say, 10 kgs, and you have 5 objects that you can carry with you in the bag, and these are the different weights of those objects, and these are the different profits that you may get after. So you want to take these objects in your bag and maybe later go and sell them off somewhere. So these are the different profits that you will obtain if you take this object and sell. And now the problem is that given you have a limited knapsack capacity of 10 kgs, how do you, which set of objects, of course you cannot take all the objects because sum of all the weights of all the objects is greater than 10 kgs. Now, which combination of these objects would you like to take so that it fetches you the maximum profit? So that is the problem. Now, this is what I just described as a simple knapsack problem. Now there are 2 variations of that. The first variation is where you are allowed fractional values. So essentially what we can see is, like, let's say if we just were to add up these value. So what we can let's say we were to these objects are there, items, and we are just, let's say, trying to add these weights. So we can see that the values are 1.98, 3.98, 8.98. So maybe we can successfully take item C, A, D, but when it comes to taking B, we cannot take, because taking B makes the total weight at 12 kgs or 12.12 kgs, and our bag can only carry a capacity of 10 kg. So what fractional knapsack gives you the freedom is, you can maybe your object be something like rice, which can be divided, rice or sugar or salt, which can be easily be divided. And so if 8.98 has been filled in your bag, and just some, I guess, 1.02 weight is pending, 1.02 kg is pending, you can take 1.02 kg from B and fill it. So that is fractional knapsack. That is, you are allowed to take fractions of fill the bag with fractions of objects also. And the second variant is where you are not allowed to fill. Maybe they are something like electronics goods where you cannot do a fraction of those objects. So another variant is 0-1 knapsack. Okay, and what we are interested in looking at here is at 0-1 knapsack. Now for fractional knapsack, the greedy solution works. So what is the greedy solution that you may ask? So greedy solution is, for every item you have some profit and you have some weight, you can simply take the ratio of profit per weight, or you can say which items gives you maximum profit per weight, and just sort those items, and based on that take all the items that give you maximum profit to weight ratio. And when you're finally an object that you cannot take completely, you can just take a fraction of it in the bag, and that will give you the optimal solution to fractional knapsack problem. But in 0-1 knapsack problem is where it becomes difficult, is because maybe you ended up taking CAD, but what if CAB may have actually given you maximum profit, or maybe ADB or maybe ADE might have given you more profit, because even though they do not have high profit to weight ratio, even though they don't satisfy the heuristic that high profit to weight ratio will ultimately give you maximum profit, but when we finally try to solve by just evaluating, we see, or let's say in a brute force manner, if we were to solve, we would find that maybe some other combination of items is a better tick. So therefore 0-1 knapsack problem becomes a little harder. And our goal right now in next few slides is to understand how branch and bound can help you to solve for this 0-1 knapsack problem without applying brute force. Of course, brute force is the worst case solution, but without applying brute force, we would like to solve in a branch and bound like setting. So any questions on understanding of what is 0-1 knapsack problem here? Okay, so everything's good, everyone's good. Vanshi, Lakshmi? Okay. Okay, because okay, I think you guys may be wondering why did I go here. The simplest thing is, yeah, the understanding branch and bound will help you to finally understand some equations in the paper. And yeah, so essentially, and of course, our main goal is not to search over all the points, but only look at some of the points. As a result, we don't compromise on the quality of solution. So branch and bound, the solution given by branch and bound is also exactly same as the solution given by brute force, but in practice branch and bound can be way more faster, because it ends up due to some, we'll see, due to some heuristics, or not exactly heuristic, but based on some bounds, it decides to not look at some of the partitions or some of the places. Or similarly here also we'll see not to look at some of the places. Now essentially, so this is our main idea, heuristic, that okay, main idea is that we would like to explore the search space. We would like to see A, B, C, A, B, D, B, D, E, explore the search space in a systematic manner and try to compute score and optimal solution using greedy search. So even though here we are trying to use solve for 0-1 knapsack, we are still going to at every element find the greedy score, and we'll try to apply bound. So, and also at every step we'll try to pick promising elements, and we'll do so by going through this 9-slide example quickly. So, okay, so what this means, we'll see that. So what that means is, let's say you start with an empty set, and so you have these 5 items that you would like to take. This table, we have sorted it by profit to weight ratio, so that it's easy to first go and take a look at the most promising element or most promising item. So definitely most promising item here means an item that has highest profit to weight ratio, because that is what will intuitively give us maximum total profit for 0-1 knapsack problem. Right, so this is how the table is formed. And now what we would like to do is, let's say we start with an empty set, and for every item in an of course one by one in a depth first search kind of pattern, we'll go through all the items. But for every item, what we ask is this question, that do we take it or do we not take it? So here, let's say we start with an empty set and we ask this question: if we take one, what will be the score and what will be the greedy score? So score is nothing but your total 0-1 knapsack profit. So let's see, if you take one in a 0-1 knapsack setting, and the best that maybe you could do in a score like setting is you could take only CAD, because that 1.98, 3.98 and 8.98, of course that's the cumulative weight for these 3 items. If you take the 4th item, it exceeds your knapsack or your bag capacity, so you cannot take that. So based on that, the score or the profit that you earn in a 0-1 knapsack setting, if you take one, is 100 plus 40 plus 95, which comes out to be 235. Now let's assume that if you were to like in a greedy setting, or let's say in a fractional knapsack setting, what is the maximum score that you would have achieved? In that case, what you would do is you would have taken CAD, and of course, I think 1.02 kgs are also pending from B. So you can take 1.02 kg fractional value from B, and also you will get a fractional profit for that. And based on that, the greedy score or the total fractional knapsack profit comes out to be 251, right? And you also maintain another variable called score bound, which is also also called as an upper bound. Score bound is essentially like it will be used to say what is the best 0-1 knapsack profit that we have so far explored, right? So when we are starting, of course, it is at minus infinity, that which means that any value, any positive finite, any finite value would be better than the score bound of minus infinity. Anyways, so let's say we started with empty set, we take one, we got a 0-1 knapsack value of 235, we got a greedy profit of 251. So this is the best we could have done if we would have taken one. And this is in a 0-1 setting, that's what we do. But let's say if we don't take one, what we get, we see that the score, how would we do? So let's say this item is not taken. That means we take 3.98, 8.98. Oh, sorry, we take weights 2 and 5, that's 7, but we cannot take the 3rd item. Now, that is this 4th item B, which means the total profit that we can make in a 0-1 knapsack setting is 40 plus 95, that's 135 if we don't take one. And in a greedy setting, we could have taken fraction of B, and that would have yielded us a profit of 182. Okay, so so is it clear, like what does take one and not take one, and what the score and greedy values mean?
What is empty set? Taking from empty set means?
So this is the initial set. So of course we'll try. So this is like we started.
We can take any random 3 things, or because it is greedy, we take the highest with profit to weight ratio.
No. So no. Are you asking about what is empty set, or why we are doing
empty? Why have you differentiated if we take C and if we don't take C?
No, okay. So what we want to do is, okay, our strategy for all these items will be that we go to every item and we see if we were to take that item, what is the best we could have done in a 0-1 knapsack setting, and what is the best we could have done in a greedy or fractional knapsack setting. And
if that item is there, okay.
So empty set means, let's say this is your knapsack bag and right now it's empty. If you were to put, let's say, item 1 in that bag, what is the best 0-1 knapsack value you could have achieved? What's the best greedy score? So that's what it means. Empty
But
set.
we then if we take one and don't take one, then we make that A and D remain constant afterwards, because A and D are the next best possible values after C. That's why.
Yes, yes, exactly.
Okay.
So essentially, we are just seeing that if we were to take one, what is the best we can do? And that's why I have this table sorted by profit to weight ratio. So if we take one, the next best is you will find that the next best would be A. It would be to take A, and then it would be to take D, and you will not be able to take B. So that's how you compute the score.
Okay.
Any other questions, Akshay, Vanshil? Neeta? Oh, okay, great. Okay, so now so essentially we are just doing computations. We'll go over all the items and try to see if we take something or if we don't take something, how that helps us. And our best goal would be to not evaluate all the pathways. Like we try to bound that. We'll see that now. In the next set, what we do is, now that let's say we have evaluated these two settings from an empty bag, we said, let's say if we take one, these are the score and greedy values we get, and if we don't take one, these are the best 0-1 knapsack and greedy values we take. So now what we do, every time we find a new better 0-1 knapsack value, we update our score bound, right? So because we found a 0-1 knapsack value, so let's say if we took one, we found a 0-1 knapsack value of 235. So essentially there exists a solution, that is where you take CAD, and that gave you the score 235, right? In a 0-1 knapsack setting. So you update the score bound variable using that. Okay. And now once you have this score bound variable, so every time you find a better 0-1 knapsack score, you update this, and every time you find for any node that the greedy or the best you can do is less than the score bound or the optimal solution you have seen so far, you bound. What does bound mean? We don't evaluate any solution beyond this point, or we don't prune. We know that an optimal solution will maybe lie in this part that may give us. So greedy kind of is giving us a window or an upper bound into what is the upper bound of profit that we can find if we go and explore in these parts of the tree. And greedy here is saying that if we explore further, the best we can do in any scenario is 182. And right now, by not just taking one, you are doing 135, but maybe the best you could do is 182. You cannot do better than 182. And since we already have a solution that gives us 235, there is no reason why we should go and explore in this part of the graph. So did you guys understand how we computed the score bound and how we bounded the searching, or how we pruned the searching of this part of the tree?
Means afterwards there wouldn't be any solution which did not consider C.
Yes, exactly. So exactly, or not, don't take one. So one means here, one means rank one item, but yeah, exactly. See, so if there is no such solution that if you don't take C will give you a solution better than if you take C. So that's why there's no need to explore further paths. Okay. Okay. So fine. So let's then explore further. So we have been saying we explore further in the tree. Let's see what does it mean to explore further here. So essentially, let's say we explore further. So now let's say we have taken one in our knapsack. So now our empty set becomes, our knapsack contains one. So at this point, or in this node of the tree, we say that we have taken one. And now we say, okay, let's say if we decide to take A or take 2 or not take 2. So how does that change our fractional knapsack and 0-1 knapsack values? Of course, if you take 2, again, you are going to take 3 and you will not be able to take 4, and your score is 235 and your greedy score is still 251.24. But if you don't take 2, That is, you have taken 1, and if you don't take 2 means you are going to go and take 3. So that becomes 1.98 plus 5, which is 6.98, and then you go and take 3.14. So this, adding this will again overshoot. So you cannot, you can. Sorry, you can. So, okay. So, yeah, this is not there. So 1.98 plus 5, 6.98, and this. So essentially, if you don't take 2, you end up taking 3 and 4. And if you take 1, 3, and 4, you are seeing 100 plus 95 plus, no, sorry, you cannot take 4. Extremely sorry. So because 1.98 plus 5 plus 3.14 sums up to a value greater than 10. Therefore, if you plan not to take 2, and if you have so far only taken 1, then you can only take 3, and you cannot take 4 because it will be infeasible, like it will exceed your knapsack value. So therefore, your score becomes 195 because you have taken 1, not 2, and 3. 195. And the greedy value, of course, can take a fractional value of 4. So the greedy value here is 243. Okay. And at this point, we can see that the best score that we have so far achieved is still standing at 235. Therefore, we don't update this. And we can see that the greedy scores at both these two nodes are higher. That is, both these nodes can probably give us a better solution than the optimal solution we have so far. So we don't bound any of the solutions. We'll need to explore both these nodes. But anyways, what we go is, in this kind of a setting where we have not bounded, or we have more than 2 prospective paths, we go in the most promising path. So most promising path being the path that has the highest greedy value. And this has the highest greedy value. So we go further and explore this. Any questions? Okay. So yeah, so we further explore this, and by exploring this means we have taken so far 1 and 2 in the node, and let's say if we take 3, then we get we take 3, the score is again 235, greedy is 251.4. If we don't take 3, then we have already taken 1 and 2. Yeah, then we probably end up taking, okay, we have taken 1 and 2, and we can take up 4 also. 3.14 plus 2 plus 1.98. So you can take this. In that case, your score comes out to be 50 plus 40 plus 100. That is, your 0-1 knapsack comes out to be 190, and your fractional knapsack, where you can also take a part of 5. You have not taken 3. You have taken 1, 2, 4, and a part of 5. Your greedy score comes at 218.8. But at this point again, you can see that this greedy has a higher value than the best solution so far, but this greedy score does not. This so here we bound it, and without any confusion, we go further and explore this part. So far we have taken 1, 2, 3. We have so at this point we have so far taken 1, 2, and 3. Now what we do, we try to take 4, but taking 4, like we have said, is infeasible because it exceeds your knapsack bag capacity. So let's say if you don't take 4. So of course, either you take 4, don't take 4. Take 4 is not feasible, so you don't look here. If you don't take 4, then you again try 2 settings. Take 5, don't take 5. Again, taking 5 will exceed your knapsack capacity, and that's a not feasible solution. You don't look at it. And then if you don't take 5, you finally get in your, so now you have finally reached your this leaf node, where you see that you have actually taken 1, 2, 3. You have not taken 4, not taken 5, and your 0-1 knapsack value is at 235, and your greedy value also saturates at 235 for this point, right? Or in some sense, you stop here, or you bound it because you have achieved the best possible solution here. So why is greedy here? Because by take 1, take 2, take 3, don't take 4, don't take 5. After that, there is no other items to take. So the 0-1 knapsack and greedy both will give us the same solution. Okay. So are we clear how we came?
Why can't we take more than one item? Means why can't we take 2C?
Why can't we take
C 2 times?
No, we have just 1 item of C. If we had 2 items of C, we would have definitely, let's say we would have maybe made weight either
Make the weight multiply
into 2.
That's why it's called 0-1. You either take one or no?
Yeah. So
One.
yeah, correct. So you could have another row here for C if there were 2 items of C.
Each item is present in only one quantity in 0 1.
No, it's okay. But if no, that's not necessary. You could have more than one items, more than one same items to choose from. As in your row, in your this in your row, you could have multiple C's.
Yeah, we can have it.
Yeah, just that they will be tied.
Problem.
Yeah, standard. I mean, in general, we don't see, but the problem allows.
Yes.
You can solve even if there are multiple rows of C. Yeah, I mean that's what I'm saying. Okay. Any other question? Okay. Okay. Fine. So now, okay. So now you remember that we have so far explored the complete part of these three. Either we have bounded at some of the nodes, or we have reached the leaf solution, or bounded because of the score bound or because of infeasibility, and either we have reached leaf solution. Now we can see that this part of the tree has not been explored yet. So let's go further and look into that. So so far at this point you had taken 1, but you had not taken 2, and you had a 0-1 knapsack score of 195 and a greedy score of 243. So let's find further. So we have taken 1, 2. Now we can draw 2 paths again. Let's say if we take 3 or we don't take 3. So if we take 3, we'll evaluate that the score is 195 and greedy score is 243. But if you don't take 3, that is, so far you have taken 1, not 2, not 3, means you'll end up taking 4 and 5, and which means 100 plus 50 plus 30. So you get a score of 180, and the greedy value comes at also 180. Now, since we have a solution better than that, we bound this path, or we don't further explore here, and then now we go on to further explore at this part. And if you take 3, then again we have option of taking 4, not taking 4. If you take 4, it's infeasible, and if you don't take 4 also, the score and greedy value also both come out to be 225, and you can bound it because your score bound was at 235. So in this case, it so happened that the this path, take 1, take 2, take 3, don't take 4, don't take 5, directly. So by going and searching in the most promising paths, how did we know most promising? We definitely followed a heuristic of which are decided as most promising, and also and also we had an ability to calculate greedy score or upper bound, and we were also maintaining what is the best solution we have found so far, and we can keep on exploring that, right? Okay, so that is how we finally have explored the complete tree. The good thing that we can see is that here, let's say we bounded here, we did not explore this part of the tree. This part of complete tree or complete part of partition we did not explore at all. Like after don't take 1, should we take 2 or not, take 3 or not? So lot of the computations have been saved by using this kind of a branch and bound solution. And we find that the maximum profit you make is 235, and the total weight in your bag is 8.98, which is less than or equal to your knapsack bag capacity. Okay, now after revisiting branch and bound, what we'll quickly try to do is adapt it to our cartographer. So how has now, so if you remember your original problem, our goal was to so these are the different grid points that we would like to evaluate.
I did not understand what is the bound. How did you stop it?
What is this bound?
Yeah, like here score is 180. So why you didn't explore it any further?
Yeah, so when the score here was 180, we did not explore it because we were maintaining a score bound variable. And what score bound variable saves is that what is the, let me show you here. Yeah, and what score bound variable saves is that what is the best 0-1 knapsack profit solution that we have found so far. Right. So let's say if we started in this like setting. So if we were to take 1 and not taking 1, The
best solution was 235.
235. That's why we updated it once here for 235.
Wait.
At 180.
See, here already score is 195.
Right.
Don't take 2. So you shouldn't have explored there itself.
No. But if you look at greedy, greedy is saying that, yeah, 0-1 knapsack score by not taking 2 is 195. But it is not checking everything down below.
Yes, correct.
It's just taking not take 2, and I'll follow the heuristic, that is, if I don't take 2, I'll maybe take 3 and 4. What if not taking 2 and maybe 4 and 5 would have been an optimal solution?
The same logic.
Yeah, so that's why that could have been. So the upper bound of all the possible paths that are possible is given by this greedy score. So if I got a score of 195 here, if greedy is saying me 243, it is saying that probably if you go down the path, you may see a 0-1 knapsack value that is more than 195, and the upper bound for that is 240. But you cannot see a value more than 240. Yes. So the upper bound of, let's say, this node, the upper bound of all the scores that are possible below this node is obtained by greedy. You cannot do better than greedy for 0-1 knapsack solution. Okay. Yeah, clear on that? Very good. Great question. So the key point to make this branch and bound work is essentially for here also. Now, what we would also like to do is we need a way to figure out how do we travel through each node, what kind of heuristics to look after, and how do we compute these upper bound. Once we have that, we can simply apply branch and bound and solve that problem. And that's what even Cartographer does. So we'll quickly go over that. Now, if you remember, our original problem was in this slide. Yes. In this slide, our original problem was we would like to find such a pose point, epsilon, in this search window, grid search window, such that if I put that epsilon in this equation, and for all the scan points, if I get that for that epsilon value, for all the scan points k equal to 1 to capital K, I get the whichever epsilon gives me the maximum value, that is my epsilon star. Okay. So that is my actual pose estimate between previous and next pose, right? So yeah, and the issue here was we were discussing was that here I would in a naive fashion I would have to evaluate on all of these pose points. That is, let's say take this point 0.2 comma 0.2 or 0.18 comma 0.2 and substitute that value here and check what value am I getting for this equation for this point, and whichever point gives me the maximum value, that is the solution. But in a brute force setting, we would have to go and evaluate on all the points. So let's say this was, let's say 10 cross 10 cross 10. So we would have to do 1000 evaluations. Now our goal is, instead of doing 1000 evaluations and then doing a max across all the evaluations and then seeing which epsilon gave me max, instead, so my goal is to find such an epsilon that could give me max. What if we could partition the set of points or the grid points repeatedly? So let's say first, when we try to partition first time, we partition it like this, and then second time when we partition it here second time like that, and then third time we can like at height. So let us say that there we are doing partitioning at different height. At height 1 we are partitioning it at height 0. This is the complete partition. At height 1, these are the 4 partitions. At height 2, these are the 16 partitions, and then it keeps on scaling 16 and then 64 partitions until we finally get the smallest partition, that is this. Now our goal is, instead of trying to evaluate for all of these small partitions or all these grid points individually, what if we could actually just do some form of an upper bound? If we knew that maybe that for this partition, the upper bound is that is upper bound or the greedy score is let's say less than the score maybe we have seen so far here, then maybe we can stop exploring. So as a result of this, let's say based on that, if we could do that, then if we using that upper bound and the optimal using the
Vanshil Shah is raising hand.
yes, Vanshil.
How do we decide the height of nodes? How are you arranging them in according to height?
Yeah. Okay, great, great question. So simply speaking, the height of nodes is you have the height such that your smallest partition becomes your grid point. So let's say here you started off with 10 cross 10 across 10 kind of a setting, and let's say in 2D you have a 10 cross 10 node. So you partition your 100 into 25, 25, 25, 25. Then you partition at height 2 by 4, you partition into 6 points, then again you partition. So here maybe you will get a height of 3 or 4 until the smallest grid point, smallest partition itself becomes the grid point. So let's say you partition it here further, okay, and then you partition it here further. So here I think the height would be, this is 1, this is 2, then this will be 3, and then this will be 4. So here the height is 4. At height 4, your partition is nothing but the grid point itself directly. Okay. Yeah. Okay. Great. Okay. I think you should interrupt me in the middle because I'm not able to see the raise hand option. But yeah, anyone can point me that. Okay. Just a minute. I should plug it in. Right. Okay. So our goal is to now, how can we find the upper bounds for a partition so that we can just completely, if we were to reject this partition, and this partition, so instead of maybe evaluating on 100 points, that is 10 cross 10, let's not, we are not going deep into the how the partitions. So we are not creating partitions on the theta right now. We're just creating partitions in x-axis and y-axis. And so let's say we have 100 points in x and y that we would like to evaluate. And if we could use an upper, we could use a greedy score and upper bound like this, and a score bound that is the optimal solution, maybe explored so far intelligently. Or maybe in some way, if you are lucky enough, maybe we can reject these part of partitions, and we instead of evaluating on 100 points, we may end up just evaluating on 25 points, or maybe even a smaller section, just 12 or 13 points instead of evaluating. So you get huge reductions in computational cost without any compromise in the optimal solution. That's the global optimal solution, or near global optimal solution, that the brute force was guaranteeing you. Okay, so that's what we would like to do. So how do we do that? So we have gone through branch and bound, how the things work. Now what our goal will be, so we would like to do node selection. That is, we would like to, like we were doing there, take one, not take. We would like to see, we would like to do a node selection or visit the children, or each partition being called as a children in a DFS similar to branch and bound. And we would like to again compute upper bound score for each child, and then we visit the most promising node, something similar to what we were doing. We will so on every partition we'll find what is the upper bound for this partition, upper bound for this partition, this and this, and whichever gives you the best upper bound, visit further into that. Okay, and at any point, if we have maybe explored some point first, and so let's say here, yeah, once we reached a leaf node, we found that, yeah, this is the 235 that we would like to go for. And of course, what I've actually explained you is a little different variant. So typically how branch and bound works is, at every node you keep on calculating your greedy score and you explore further or not. And once you have reached a leaf node, then only you go back here and update your score bound, that once I've reached a leaf node. So that is what it means, that it first does a depth first, and then finds an optimal solution depth first, update this, and then maybe bound apply bounds here and here. But I think while explaining, I was also calculating what is the score that you could have got, and I was applying bounds also quickly, so that if we can update this quickly, we can apply bounds also quickly. But sometimes, like we'll see in the case of cartographer, you may not be able to calculate a score at that. Maybe okay, we may not be able to calculate a score here. All we could calculate is the upper bound, and only when we look at this point or maybe at this point we can calculate that score. So only at that point we can start applying the these kind of bounds or prune away some parts of the partition that we like to search. Okay, so yeah, so essentially, okay, and like we said, the branching rule is nothing but your that each partition is divided into 4 parts. Okay, so let's say at height 1, the node will be this, and this, and height 2, the nodes will be at this. Okay, actually you can consider it center, or you can consider the left bottom part of the node representing that partition. So here at height 1, your nodes would be at this, and this, and at height 2, inside height 1, the nodes would be this, and this. So WC bar or C kind of denote that at node at some height h is So essentially your WC is saying how does your grid look at that height. So at height 1, your grid is of course it will typically look as a grid which has just 4 points at any I mean, of course here it looks like a grid with 4 points at height 1. At height 2, it would look like a grid that has 16 points, like here 4, here 4, here 4, and here 4. So, and at the finest level, that is at the leaf node, your WC double bar ends up becoming the finer resolution grid. Okay, so that is you would remember seeing this, the W bar, that is the -10 to 10 and 10. So at the last leaf level, your grid becomes this, that is W bar. Okay, any questions on how we are going to proceed or how the problem is set up for finding poses? We'll discuss on how upper bound is calculated for each of the partition. But any question and the score calculation is, of course, this is the score that we are going to calculate. This is the 0-1 knapsack equivalent in our problem, and the greedy score equivalent I'll mention little later what that is. Any questions so far?
No.
Okay, fine. So okay, so here what I think I'm trying to show here, it doesn't matter a lot, but what I'm trying to show you here is, let's say these all lines are nothing. So the intersections of these lines are nothing but your grid points. Okay, are all your grid points, and let this wavy line intersections denote grid points at certain height h. So maybe it is at height equal to 2. So these are the grid points at height equal to 2, and typically when you try to write it like this as a powers of 2, sometimes of course you would, so ideally you would like I said, if this and this were in factors of 2, we could have easily kept on dividing by 2. But if this is 100 by 100, first time we divide, it becomes like this, the size of each partition becomes like, yeah, so this is 100 by 100. The size of first time it becomes 50 by 50. The next time you divide, it becomes 25 by 25. Now the next time you divide, of course, if you try to keep on dividing in factors of 2, you might actually be overlooking. At some height, you might be overlooking into other partitions part. So that is what this shows, that by using this equation or by just doing a simple partitioning, you might be overlooking. So maybe this was just your partition itself, and at this height, these are the nodes that you're interested, but these are the points that you get by overlooking or into partitions that are outside yours. Okay, and when you take an intersection of all the grid points, that the leaf grid points that you originally had, and this this overlooked points that you not the overlooking, these nodes at certain height h, let's say at height 2, and the grid points. So if you take intersection, only these 6 points at height 2 qualify. These points won't qualify because they are not part of the partition. Okay, they're just somewhere outside the partition. Maybe okay, maybe for these points they are outside here or something of that sort. Okay, so essentially I'm just trying to give you here the notations. So WC bar is all the grid points that are at some height CH, that is at height 1, this constitutes WC bar. At height 2, this sorry, this, and yeah, this. They qualify as a height at 2, and so that is what WC double bar. You remember W bar was simply each of these leaf node points that what your brute force was evaluating into, and if you take an intersection of W bar and WC bar, that is the points you would ultimately end up evaluating on, and that we are representing as WC bar. Okay. Yeah, Vansil, you have your hand raised. Any question?
I don't have interest.
Oh, okay. Oh, okay. So, fine. Okay. Any questions so far? I think this is just a terminology what WC bar is. I'll go forward. So essentially, yeah. Now here we'll show what that upper bound is. How can we compute an upper bound for this partition? Okay. So essentially, if you remember, you would like for some given epsilon. Okay, maybe this epsilon is a leaf node, or this epsilon is this
lag in video. Lag in video. I actually did not see that part where you explained the intersection of WC and WC bar. There is a lot of lag. I'm getting skipped things.
Okay. Is there lag for others? Vinita and Akshay?
I am here.
No, but
it's fine for me.
Okay. Vanchil, you can see the screen. I'll repeat again. It's okay.
No worries, but I just want to see the definition. Okay. Grid points under concentration research window. Okay, cool. Yeah, got that.
Okay. One line summary again is WC double bar is grid points at certain height CH. So essentially,
Yes, I got that. You can move further.
Certain height H, W bar was nothing but what we had initially, that is all the grid points that brute force was looking, and an intersection. So so let's say if you had a grid that was grid size that was of the size of the powers of 2, then there would not have been any difference between WC bar and WC double bar. The intersection would have been just perfect, but sometimes when it is not powers of 2, because since that's an hyperparameter, like we took here 100 by 100, yeah, this can differ, WC bar and WC double bar. And we are, even though for branch and bound, while branching we look at WC double bar, we are only interested in calculating on WC bar points. So WC double bar is this. These 8 points are WC double bar, that are nodes at height CH or height 2 maybe, and WC bar would be only these 6 points that lie in the grid of our interest and not maybe outside. So that is the only notation. Okay. Great. So now we would like to know for each partition how can we compute upper bound. So if we just look, now if we were to look at the equation, essentially what we are doing is that for every point, so for a given epsilon, that is, let's say maybe that epsilon is this leaf node here, or maybe a partition node here. Okay, that is currently representing the whole of the point, but okay, maybe for some given epsilon, we would like to we would put that epsilon in this equation, and for all the scan points for k equal to 1 to capital K of second scan, we would like to see if we keep on applying epsilon, which epsilon gives us maximum. Now we can actually change this equation, and what we can do is, so I've rewritten this equation here. So now we can convert this equation, and essentially, okay, at any point we are actually only interested in solving only for WC bar points. Like we said previously, that we are only interested in solving at certain height only for points that are at inside your own grid partition and are at certain height. Maybe not for all the points in that height, only for certain height is what you are interested in evaluating at. So this equation gets converted into this. Now, once you would like to only solve for WC bar points, WC bar points means this, only WC bar points here. Now you can convert this and say that a max of sum is actually less than sum of max. So this equation is actually less than this. Or in other words, what we can say is, if we were to find a maximum epsilon candidate argmaps, let's say maximum, if you were to fill multiple epsilons, and if you were to find the maximum value that sums over different scan points, instead of that, we would like to first apply the max, that what is the maximum value that the scan point can take, and then for all the scan points, second scan points, we sum that value. So we have just used this equation here, that max of sum is less than sum of max, and that's how we have converted this to this. And now this is again lower than, so here we have max over WC bar, and here we have max over WC double bar, and we can say this is lower than this. Why? Because WC bar captures larger search space than WC bar or W bar. Why do we say that? Because here we can see these points, these circle dot points are WC bar points. Actually, this can capture more number of points, and this has a more chance of getting a bigger max, more than what these WC bar points may have seen. So any confusion on how we arrived from here to this equation, or is everything in confusion?
The last constraint, WC double bar 1,
yes,
that is just because the number of points are more. Means suppose there is summation of 1 to 6, then it is less than 6 times 6 means less than 36. So that would be less than equal to 10 times 6, less than 60. So that 61 would be the last constraint.
Okay, something of that sort. But okay, something of that sort. Let me also maybe give another example to just for clarification. So let's say you let's say you have 10 events. Okay, you have 10 events, and in all the events you you have 10 events, and in all the events you just toss a die. You toss a die. Okay, and now let's say the maximum, the sum of maximum that you can get from all the 10 events will be lower than sum of maximum that you can get maybe from 15 events.
Okay.
Because you have more number of
events.
More number of events or points. Yes, that's correct. Okay, Akshaj, Avanchil, any other question? So now we are going to use this as our upper bound, that this is our greedy score. This is the maximum value that a partition can take. I'll show you how to calculate this, but yeah, any questions so far? Okay, I think we are good. Fine. So yeah, so that is what was there in this paper. So essentially this is the score C is the upper bound that they would like to calculate for every partition, and they say that this is obviously greater than this value, so that can act as a greedy score equivalent in the branch and bound. Now, how would we like to calculate that? Now, okay, so how would we like to do that is, what we actually do is, we also we would like to do this computations, greedy score computations efficiently. So how we would like to do is, if you remember this plot, right? And our goal is that, of course, there are at multiple heights, different. So of course, these are the final scan endpoints. By the way, please do not get confused between these points and these points or these points. So these points are, each of them are a pose candidates, like or these, this is a epsilon, this is another epsilon, this is another epsilon, and these points are the points in the map or occupancy grid or the voxels. Okay, now what you would like to do is essentially okay, so I'll just read through this and then I'll explain. So essentially what you would like to do is, essentially your this m nearest the epsilon hk becomes mch pre-comp. So pre-comp is, you can actually keep it pre-computed for each pixel in the map. So each pixel, that is your occupancy grid in the map, and at different height you can have different pre-computations, and you can therefore, if you have this pre-computations ready, you can just sum up for all those individual pixels this pre-computations, and finally get the upper bound for any given partition. So we save these pre-computations. We'll show how the pre-computations come into being, and once we have pre-computed values of the maximum that this point can go, maximum that that point can help achieve, okay, and then we'll do. Okay, so how we do that is, essentially your mh pre-comp is, this is nothing but your the max. So this max over j omega wc is being written as this. The wc is now being written as x hyphen and y hyphen, which is nothing but what you are doing is that for all the pixels in the map, let's say you are considering this map, all the pixels in the map, you find the maximum map value in the search window and set this pixel as the value. So that is for all the pixels in the map. So let's say this is a pixel, this is a pixel, this is pixel, this is pixel, this is pixel, and you find what is the maximum map value in the search window. Now for this pixel in the search window of just size of itself, the maximum pixel value is the value of the pixel itself. But now when you maybe increase the height, not the height, or let's say if you actually decrease the height or at a bigger search window, you take a maximum over this search window. That's what it says, from x to x plus r into this. You take a maximum over this search window, and then if you are looking at a bigger search window, bigger search partition, you are looking at a maximum over this pixel value. That is, what is the maximum in all this? That is the maximum pixel value that we'll try to store here. So in some sense, you could look at this as some form of doing a max pool over these points and then assigning each of these pixels with the max pool value. Okay, so that is what this pre-computation at certain height means. So let's say at some height you are going to look at these pixel values, and maybe this has a pixel value of 0.2, 0.4, 0.5, 0.6, 0.8, 0.7, and let's say 1. So for this pixel at search window of this size, this will be maybe 0.2. That was its original. And at search window of this size, since this had 0.8, its value becomes pre-computed value becomes 0.8, and at search window of this size, since this had 1, its pre-computed value becomes 1 at search window this. So for different search window sizes, the same pixel value can have different values. Now what we do that once we have these different pixel values, max pixel values are different, we just try to sum it up. And now that let's say if we are looking at a bigger partition, and for this pixel what is the max, this pixel what was the max it could get in that search window, this pixel, and then we sum it over to get the score or the upper bound for a given partition. Any question? Or is everything?
Why did we first the points shown were post candidates, right? But right now there are pixel values. Why are we doing that? Means.
Yeah. Okay. Good question. Yes. So essentially, what do you take this post candidate? Okay. Let's say your any epsilon post candidate either comes from a leaf node or maybe comes from a partition height node, maybe. Okay. Right. So you take that post candidate and then you apply the transformation on all the points of second scan. Right. For some post candidate, you apply the transformation T epsilon HK. You apply the transformation of all the points on the second scan, and now you want to very quickly get the this maximum value very quickly. So the ideal way to compute your map value on that HK point would be using this kind of a bilinear interpolation. But this is fine. This is giving you your, let's say, analogous to 0,1 knapsack value. But you also want to find that for this HK, what is the greedy knapsack value that you can achieve? So for the greedy knapsack value, you try to draw such search windows over max and get that. So that is kind of saying that in a course.
So this search window is different from the original search window.
Yes, this search window is in your occupancy grid, and that you are pixelating, and then it actually becomes and looks like this. So this is what you will use for doing the scan matching. But for pose estimate in the grid search, you use a different search window. That's your grid search window that contains only poses. Yes. Okay. So I can see that. Okay. Good. Any other question? Somewhat clear, little clear, more clear. I mean, definitely this will at least give you some intuition on what's happening, hopefully. And then maybe if you take just maybe read again the paper once, it will, everything should start to fall in the place. So essentially now, yeah. So essentially for occupancy grid, this is, let's say, search window of size 1, where each pixel, so black means occupied, white means unoccupied, gray means it's not clear. And here we can see that when the search window, which one? The occupancy grid search window is of size 1. So there is no max is happening. Max is happening over the value itself. So the values are absolutely crisp, and this is the kind of map you would like to use for scan matching. Or what scan matching? This one, the thing that we were trying to do in a brute force manner, or that at height. So this would happen maybe at height 4. But let's say at height 1, you have a this kind of a quotient map, where this set of, because this had a max, that max actually, as the search window increases, this has the highest search window, because like we can see. So we need to understand that partition at height 1 uses occupancy grid maps of search window 64. And partition at height 2, these are the partitions of height 2. So here also we have the same partitions. They will use map of map that have been pixelated by search window 60. So why do we do that? So that we can very quickly at this stage compute the search window. And then just 1 second. Okay, some noise there. Yeah. So that this. So is that concept clear? So essentially, our goal is to find which pose. I mean, by each a partition, our goal is to find which pose can best can give us the maximum value for this, so that serves as our scan matching value. So essentially, in some sense, you could see that Cartographer is actually trying to come up with a new way of doing a scan matching, a brute force, not a brute force, but in a search window in a branch and bound setting, like scan matching, so that by using this kind of scan matchings, you can very quickly find loop closing constraints also. Okay, so maybe that's the kind of summary that we are looking at. A lot of time has been spent, but yeah. So is that clear? Any questions?
Last slide थी
नहीं और एक दो.
हाँ तो recording बंद कर दो ना यार.
Okay, ठीक.